Yeah.
The camera's not very focused. Is there a way to? There, that's better. Yeah. Okay, let me start again. We are not gonna cover anything new next Tuesday. I'm just gonna review, get you ready for the exam that opens next Thursday. I have posted 2 sample exams at Matt's as well as their solutions. And also, of course, the homework solutions are there. As far as the review session next week, I figured Wednesday night, the night before the exam opened, would be the best time to do that. It turns out this room is booked that night all evening. And so we're going to be over in the Clyde building, the big engineering building, and the big lecture hall on the 3rd floor, 377. Now, before we get started on today's topic, I just want to cover some of the ideas that we covered before, but the demos were a little less than convincing. Clark and I went out and spent some money and got some more coils that are beefier than this one here. And you remember that I told you that the number of turns, loops in the coil mattered a great deal, that we had to multiply all of the field lines that go through the coil. We have to multiply by the number of loops in the coil. So this one has very few loops, and you see that when I change the magnetic flux through the loop, I get a little wiggle there. If I take this new coil that has 200 loops, was it bigger? Okay. And now if I take this Mondo one that has 500 turns, is it more bigger? Yeah, I'm pegging it. Okay, so NBA, National Basketball Association, the N is for the number of loops. The other thing I'd like to share with you is this Pepsi Cup speaker was working when I introduced it to you the other day. You could hear it. You claimed that you could hear it. I couldn't hear it because of my damaged ears. But I've been working on it, and I've made it also more better. So that's not better.
It's not playing.
What's that?
It's not playing.
It's not plugged into what?
It's not playing.
Oh, it's not. Okay. There we go. Can you hear that? Oh yeah. Even I can hear it. Okay, I think we should sing this morning. And so let's sing a song. Okay. I guess I better get this started at the beginning. Singing. Like a sings of all returning. They don't call me to visit the earth. We'll sing and we'll shout. If you want me some heaven, Hosanna, Hosanna. In the heart, begin henceforth and forever. And amen. Okay, have you ever sung to a Pepsi cup before? Oh, could be willing to give us an opening prayer this morning. Thank you.
Kind of gracious Heavenly Father, we're grateful for this day, we're grateful for the opportunity that we have to learn more about physics, and we're grateful, Heavenly Father, for Professor Francis and all that he does to prepare these lessons, and we're grateful also for his loving care. Heavenly Father, we're grateful for thy Son, Jesus Christ, for his sacrifice for us. We ask that you please help us to be better disciples, and please help us to retain this information as we prepare for the test. Say these things in the name of Jesus Christ.
Amen. Thank you. Okay, let's start with a pop quiz. Why not?
This one going towards. Wait, what is the red? Free is it's gorilla, and it goes to the fourth part of your.
It is no. I don't think so. But if you look at their webpage, it'll give you the hours. But I think both days there was. Yeah. But Thursday, Monday, and Tuesday are definitely on. Okay, last call. This is an easy question. Okay. Good. Okay, we're on the bus. We're on the bus. It is right-hand rule number 3. Okay. Now, really quick, let's review what we learned about generators. We learned that anytime I change the number of field lines through a loop, I generate this magical current that we can't see the battery of. The battery is given by Faraday's law. Now, I can change the number of field lines through that loop, either by making the loop smaller, making the loop larger, bringing a stronger magnet near, or bringing a magnet closer so that the magnetic field's stronger. Or I can change the area that the magnetic field lines see by rotating the loop, okay? And by rotating the loop, I get field lines going through. If the field lines are going towards the piano, I get field lines and then no field lines, and then field lines and then no field lines. Now, that's going to induce this current that we light up our cities with. And we found that that current is always going to show up in such a direction that it's going to fight the motion, that we're going to have to do positive work to pay for that current. If we want to light up our cities, we got to pay for it. And so we have to have something like falling water off of the hydroelectric dam to turn these coils. And so what we see is that nature, the laws of physics, is going to set up that induced current. That's what the green X and the dot mean, that the current's going to go in at the bottom and out at the top, and that's going to cause a dipole. Now, any dipole, any bar magnet that's free to rotate, is going to want to line up with this external magnetic field. It's going to want to point towards the piano, but we're forcing it the other way, and that's why we have to fight. And as soon as we get here, well, if the current kept going the same way, now that current would be turning the coil, trying to line up. But nature says, oh, no, you don't. You always have to fight. So it changes the direction of the induced current, so that again, you have to fight as you go around, and then changes the direction again, and you have to fight all the way around. Now, we discussed the fact that anything with a motor in it has coils, and those coils are turning in an external magnetic field. But in a motor, we have battery current, and that battery current we can control through engineering. We can decide with the commutators when it's going to go one way around the loop and when it's going to go the other way around the loop. And so we always make that current go in such a way that the dipole created by that current is trying to line up with the external field. That current from the battery is causing the rotation. But as soon as the rotation starts, I got a loop turning in an external magnetic field. That's a generator. And that's going to create a second current, the induced current. And that current is going to go the other way. That current's going to fight the motion. The red arrow is causing the motion. That's from the battery. The green arrow is fighting the motion. We call that the back EMF, or the back voltage. Okay, and you see that as it goes around, we change right here, we change the direction of the red arrow with the commutator, with those bushings. That just, you want to see that again? Pow! Okay, but nature changes the direction of the green arrow. And then it just goes around. The green arrow is always fighting the motion. The red arrow is always causing the motion. Check to see if your neighbor is on the bus, please.
Because the change is going one way, then you come off it, and I was fighting.
Okay. Now, it turns out that this back EMF is really a good thing. Okay, and that's because if there was no such thing as this back EMF, then when you plugged in, say, a hairdryer or a fan, you would get a constant torque from the motor. And that constant torque, we learned in 105, is just going to speed up the spin rate of the fan blades or whatever's spinning around in your hairdryer. And it's going to speed it up and speed it up and speed it up and speed it up with no limit. Well, speed of light, okay? But with this back EMF, that back EMF depends on how quickly that coil is turning. And so when the coil gets turning fast enough that the back EMF is almost equal to the voltage of the battery or power supply, then we get this steady state where the current, the net current is just enough to overcome the friction. So let's look at these questions up here. I've got a coil of an AC motor and it has a resistance of 4 ohms. The motor is plugged into an outlet where V is equal to 120 volts and the coil develops a back EMF of 118 volts when rotating at constant speed. The motor's turning a wheel, we don't care. What's the current when the motor first starts up, when you first plug it in? Well, V equals IR. Okay, so I've got 120 volts pushing current through 4 ohms, and that gives me a current of 30 amps. Okay, that's a lot of current. You know, you really don't want that much current running through the hairdryer in your hand there. But very quickly that gets turning, and now when I do V equals IR, my V is going to be the 120 volts from the wall pushing one way to make the motor turn, minus the back EMF that nature provides, and that's going to give me I times the 4 ohms, and that's going to give me an I of 1/2 amp. Okay? And that's important because your appliances, like that hairdryer, were not made to handle 30 amps. They're made to handle 1/2 amp just fine. But the 30 amps, that's only there for just a split fraction of a second while it's starting to spin. Okay. An example of this, my redheaded son, who became the orthodontist and is rich, when he was young, it might not surprise you to learn that he was always interested in money. Oh, he loved the money. And so he would do any chore for money. And as parents, we felt it our responsibility to take advantage of his youth. And so we would give him big chores and give him a quarter, and he was so happy. But I told him one day that I would give him 50 cents if he would vacuum out our old Chrysler Cordoba, 1979 Chrysler Cordoba, big land yacht, huge hood. But we couldn't open the hood. And that's because in pulling the little lever inside the car to release the hood, the cable had snapped. And so right behind the gas pedal, there was this metal cable that was just kind of hanging there. And, you know, that's not really safe, but hey, it was an old car. So Christian's out there dust busting this car, and suddenly there's screaming, there's yelling. I come into the garage, there's smoke, there's fire. What had happened is he had just dust busted, you know, with a corded dust buster, dust busted up this cable, and it jammed the cable. And so now, instead of turning, I just had current going through these coils with no back EMF. So instead of 1/2 amp, we got 30 amp, and it just burst into flames. So I had an opportunity to teach my young son physics, and it only cost me 50 cents. Okay. That might be on the exam. I don't know. Okay, another pop quiz. You remember the magnetic field due to the Earth looked like this, where magnetic field lines came out of the South Pole, Antarctica, where the penguins live, and go down into the Earth up here in the Northern Hemisphere where we live. And so if you live in Antarctica, the field lines aren't going into the pavement, they're coming out of the pavement. So when you drive your car over this smart light, the little wire loop that's in the pavement in the road in Antarctica, busy streets, you know, does the current flow clockwise or counterclockwise with your clicker, please?
It is, so that's technically the north. Going up, so I think it'd be. Yeah, I agree.
Okay, last call, get it done. Get your points. Whoa, okay. We have not mastered this yet. That's concerning, okay? So without a car, the field lines are coming out through that loop, up out of the pavement, okay? Through the loop up. And when we drive a car over there, its engine magnifies that. It increases the number of field lines because it's got a magnetic field aligned with that external field. So instead of 5 field lines up, I now have 65 field lines up. How are we going to fight that change? We got to send field lines down. And if they're going down, my fingers are telling me which direction the induced current is going to flow to send those field lines down. It's clockwise. And clockwise didn't even win. Okay, that worries me. That worries me. Okay, are there questions on what we're doing there?
How do you know if you're trying to find the induced current or like the other current?
I'm sorry.
How do you know if you're trying to find the induced current or the other current?
In this particular problem, there is only induced current.
There's no battery hooked up to the.
There's no
cord.
battery.
No battery.
There's no battery. It's just a loop of wire. Yeah. So, for example, in this example where I had this coil here, if I were to hook this coil to the battery, that would be battery current, and it would have a dipole that would be given by right-hand rule. But when I just change the magnetic flux through the loop, no battery. There's only one flavor of current. What you're seeing on this dial is the induced current, because it's not being generated by anything that I paid for. Okay. Other questions? Okay.
Dr. Francis,
Yes.
could you remind us again how we know that driving your car is gonna increase the fuel lines up? How do we know it's increasing it up?
Well,
Or the same
The-
direction as that?
if I take a hunk of iron and put it in an external magnetic field, we found that that magnetizes the iron. And it magnetizes the iron in the same direction that the external field is pointing. The little atoms of iron act like little compass needles and line up. And so if the Earth's magnetic field is up, so will the car's magnetic field be up.
Okay, I think it was on the south higher than orbital, then it'd be the opposite.
That's right. Yeah, last day we talked about what would happen in Provo, and then we were increasing the field lines down when we drove the car on. And so we needed induced current, induced flux up, and the current had to be counterclockwise. Now, I could also ask, say on an exam, what happens in Provo when you leave the loop? Yeah, when you leave the loop, you're going from lots of field lines down in Provo to just a few field lines down. And so I've got to fight that change by sending some more down, and I get clockwise. Okay, was there another question, or you were raising for him? Yes, sir.
So when you say it has to fight it,
And there's one current and it's fighting, like, what is it fighting then? Is it fighting the change the magnetic field?
It's fighting the change in the magnetic field line. Okay, not necessarily the change in magnetic field. Remember, I can change the number of magnetic field lines by either changing the magnetic field or changing the area, either one. But if I go from 5 field lines through that loop to 25 field lines through the loop, that's the change that it's fighting.
Then why does it need to fight that?
Why does it need to fight that? To conserve energy. We found that that induced current has to be paid for. Okay. And we're glad that it does, because otherwise we wouldn't have magnetic induction. We wouldn't be able to light up our cities like we do. Okay. Let's move on. Oh. So clockwise was the right answer here. We just have a couple of big ideas to cover before we're done with this part of the class and ready to take that third exam. And I'm going to start by talking about mutual inductance. And what that means in a nutshell is how tightly are two coils connected to each other. Okay, so if I hook this primary coil on your right to a battery, whenever I close the switch here, I put current through this coil. That's going to change the number of field lines through this coil over here, the secondary coil. And by changing the number of field lines through the secondary coil, I create this magical, can't see the battery current. And we see that on this ammeter. And so you see that when I have these coils far from each other, when I close the switch and open the switch, first of all, Greg, you senile old man. Yep. Just a matter of time, people. Then I'm going to be just wandering the streets. Okay. I knew it was coming. Okay, so I'm closing the switch and opening the switch, and you're seeing it wiggle, right? Okay. Now, I'm not changing the number of field lines through that loop by very much, because the field lines created over here, remember it acts like a bar magnet, they spread out. And this is so far away that not many of those field lines are making it. But if I get that coil closer and do it again, I get a bigger deflection. And if I put them really close, now I'm getting a big deflection. Now, another way I can increase the coupling is what we're talking about. When I say mutual inductance, I'm asking how coupled are these two coils to each other? When this one has field lines through it, how does that affect the other coil? How many field lines does this one get for the field lines over here? Now I can increase the coupling by taking an iron core and putting it between the two. Now we know what happens here. When I put current through this coil, I'm creating field lines due to the coil, but I'm also magnetizing this piece of iron. And that's creating field lines as well. And so now, even though they're far apart, I still get that large coupling because of that iron core. And if I put them close together with the iron core, now I'm pegging it. I'm going to break the thing. Okay. I don't want to, but it just seems so fun. Okay. So that's what we mean when we say mutual inductance, is how tightly are these coupled to each other. Now, let's do some math, just a little bit. We say that the flux, and when I say flux, I mean the number of field lines through this secondary coil is proportional to the current through the first coil. Okay, if I double the current through this coil here, I'm going to double the number of field lines that make it through the secondary coil from the first coil. Now, whenever I have this proportionality, this fish symbol, I can replace it with an equal sign if I put a constant of proportionality. And that constant of proportionality, that capital M, is what we call the mutual inductance. Now, I can rewrite that equation by dividing both sides by I1. And I can say the flux in 2 divided by I1 is how I define my mutual inductance. Now, that's a division. Whenever we have a definition that is a ratio, something divided by something else, we set the basement equal to 1. And that gives us a gut level feeling for what it means. Flux is just the number of field lines. And so the mutual inductance is just how many field lines do I get through that secondary coil for every 1 amp that I put through the primary coil. For every unit of current, 1 amp that I put through the primary coil. Talk to your neighbor, see if your neighbor's on the bus.
That's how many field lines area is.
Now, I hope it's apparent to you that there are several ways that I could increase the mutual inductance, and I showed some of them here. If I increase the number of turns in the primary, every time I put 1 amp through this thing, I'm creating a stronger magnetic field with more turns, okay? And so that would be one way to increase the mutual inductance. By putting more turns in the secondary coil, every field line that gets sent over by the primary, I have to count for each loop. And so if I double the number of loops in the secondary, I double the flux that I'm counting. And then, of course, if I put the iron core in, that's just gravy. That just gives me more field lines because of the magnetization of the iron. Now, if I plug this into Faraday's law, remember, Faraday's law says that there's going to be a magic battery set up in this secondary coil that's caused by the change, the time rate of change of the flux through that coil. Well, if I plug MI in instead of the phi2, what I get is that. And what I see is that the induced battery in the secondary coil depends on how coupled it is to the primary and how quickly I change the current through the primary. Okay. Now, I'm sorry to say, I'm a little embarrassed to say that that's not really what we're going to be caring about on the exam. Okay, that's not where the fun is. I needed to present that to you to get you ready for what comes next. And what comes next, I'm going to introduce with this little exercise. If I have this circuit sitting on the table, and you remember that the positive end of the battery is the one with the lump. And I only say that because every exam I've ever given, I've had that question, you know, which side of the battery is the positive side? The one with the lump, okay? And that's creating a certain current, battery current in that loop. And the question is, if I bring down the North Pole towards that loop, is that going to increase or decrease the total current in the loop? And let's do one more clicker question here.
So that's already had.
Okay. Get your vote in. Last call. Okay, good. The answer is decrease. Decrease. The battery current, conventional current, which we always talk about, leaves the positive terminal and goes to the negative terminal. So it's going around that loop clockwise. If I bring down a North Pole, I'm increasing the number of field lines through the loop down. That means we fight that change by sending induced field lines up. And to send induced field lines up, I need induced current counterclockwise. And so that's going to fight the battery current, and the total current is going to be the red minus the blue. Okay? And so the answer is it will decrease the total current. Now, what if I had brought the South Pole down instead of the North Pole? Well, then the induced current would be clockwise, like the battery current, and I would be increasing the current in the loop. In this experiment, I can make the total current bigger or smaller. But it turns out that when I just have a loop and I try to change the current through that loop, I don't get the option of increasing or decreasing the current. It turns out that when I have a loop in a circuit, it fights any change in the current. Now, let me back up a little bit. Up until now, I've been making a big deal about external flux and induced flux. External flux is due to everything that's not the coil, and induced flux is what happens when there is a current in the coil, an induced current. It turns out that coils can't see. They can't tell external flux from induced flux. They just fight flux. Okay, and so when I close this switch, I'm going from no field lines through this loop to lots of field lines through the loop. That's a change in the number of field lines through this loop. And it's going to fight that change. It's going to fight that change. And so we call this self-inductance. And let me just point out that if I've got a whole bunch of wire going round and round and round and round, we always talk about our wire being perfect, our wire being, you know, really, really made out of platinum. You know, it's really, really very easy to get through. But real wires have resistance. So we often separate out these two components. This is the resistance of the wire, and this is what we call the self-inductance. Yes, sir.
Yeah, I thought we had learned that the induced flux is always lesser than the external magnetic flux.
It's always lesser than the change in external magnetic flux. The change. And the only exception that we found the other day was when we got that superconducting material down to where it had zero resistance, so that we couldn't change the number of field lines through the loop. That's when we pinned the field lines in place, and that's why it hovered there above the track. Okay. Now, the units of in self-inductance and mutual inductance are henries, again, to honor a dead physics professor. Let's go back and do what we did with mutual inductance. We find that the flux through a single coil, just this one here alone, all by its onesies, okay, that is proportional to how much current goes through that coil. Now, again, I can replace that proportionality with a constant and an equal sign. We call that the constant of proportionality. And this particular constant we name self-inductance. Now, folks, before I go any further, you might think that you don't care about coils and this self-inductance. But as I've said before, there are very, very few elements that go into an analog circuit, whether it be a stereo, a TV, or anything. You've got your resistors, your power supply like the battery, you've got your capacitors, and you've got your inductors. And that's it, unless you count a switch as an element. And so everything that you, everything that we had before we had digital electronics was made out of those five things, okay? And so it's an important idea that you'll see coming back over and over again. Now, if I go back to Faraday's law and say that the EMF created, the induced EMF created in this primary coil, that would be the back EMF, okay? That is equal to, the minus sign means fights any change in the flux through that coil, the time rate of change. And so if I plug that into my formula, I get this. There's an invisible battery that gets set up that will fight any quick change I make in the number of field lines, and hence the number of amps through that coil. So if I try to change the current through a coil from, the coil always fights a change in its own current. If I try to change the current in a coil from nothing to something really quick, it fights me, okay? If I try to make the current go from nothing here to say 3 amps all at once, let's see what that magical battery looks like. Let's plug in the numbers, shall we? The battery is going to equal to whatever this self-inductance is. That's just a number, okay? The change in current, I went from 0 to 3, so that's 3 amps, and I did it in no time at all, so I divide by 0. What do I get then? Infinity, infinity. So there's no possible way that I can make this current in the coil go from 0 to 3 all at once. Instead, I have to ramp up the current gradually, exponentially. But if I look right after I close the switch, right after I close the switch, I still got about the same as I had right before I closed the switch. It takes time to ramp up. And if I don't give it any time, it's still 0. Does this seem familiar? You remember when we were talking about capacitors and we said when I throw the switch closed, it was empty before I closed the switch. It takes time to fill up the capacitor. It's still empty. Well, here it's the current that can't change instantly. Now, that's also true when I try to turn the current off. I can't just make the current go from 3 amps to 0 amps all at once. That would generate an infinite battery by Faraday's law. And so I've got to gradually ramp down that current. Now, I think that most of you have seen this in your life. How many of you have a waffle iron? Come on, people, you gotta have a waffle iron. If you open up a waffle iron, you see that it's got a bunch of heating coils in there. Coils are coils. Coils fight any change in their current. And so when you unplug a waffle iron, what you see at the wall is a great big old spark. Okay, and that's because it had a certain amount of current flowing through that coil, and you were trying to make that go to 0 all at once. Well, through Faraday's law, an invisible battery was set up that said, oh, no, you don't. Oh, no, you don't. And so it kept the current going right through the air in the form of that spark so that it was brought down more gradually. Okay. Now, this experiment, I hope, works. Let's see. Not sure how good it's going to show up.
This power supply puts out about 6 volts. When we touch the output leads together and separate them, no spark is seen. If we hook the leads to this solenoid coil with 2,000 turns of wire and disconnect one wire, a small spark is seen. When an iron core is inserted into the coil and the sequence is repeated, a larger spark is seen.
Okay. Now, Clark, bless his heart, spent pretty much the better part of yesterday putting together this demo for us. It's a demo that I had back in Montana, and I said, I really want to do this demo, Clark. And so he went out of his way to make it. And what we've got are 2 branches that are independent across the battery. Okay. When I hit this button here, we're going to have about 24 volts across this loop and across this loop. Now, what you see in this loop are 2 bulbs in series, and this one just has 1 bulb. And you're thinking, oh, Greg, that's not fair. That's got 2, that's got 1. But this loop also has an inductor, a coil of wire. And it turns out that we had to very carefully find a coil that had almost exactly the same resistance as a bulb. And so this has a resistance of 2 bulbs. This has a resistance of 2 bulbs. The only difference is, in this case, the resistance here is wire going round and round and round and round. Now I have a double pole, double throw switch here so that I can turn on the battery and nothing's on because the switch is open. But when I close this switch, what you're going to see is that these bulbs that are just by themselves are going to light up immediately. This one, it's going to take a little bit of time. It's just going to, there's going to be a little bit of a lag. So, ready? I'm going to close the switch now. You see the delay? Okay. Did you hear that pop? That was the spark. Okay. So watch it again. You saw the delay. Okay. Now we could increase that delay by having more inductance. We call it inductance instead of self-inductance. It's just shortening the name. If we added more inductance, it would delay it even more. Now, some of you right now are learning exactly the wrong thing from this demo, okay? You're there thinking, well, sure, Greg, it's going to take longer for that bulb to light up because this wire goes round and round and round and round and round and round. And by the time that current gets all the way around all those turns and gets to the bulb, there was a delay. That's not what's happening here. If I unwound this wire, and let's say it's 6 miles long, and I lay it out flat, straight line, you know, to Springville and back, okay? I close that switch and both circuits, both branches light up all at once. There is no delay. It has nothing to do with the length of wire. It has everything to do with the fact that the wire's going in a loop. And because it's going in a loop, it's fighting that current change. Not fighting the current, it's fighting the change in the current. The change in the current. Now, if we go back, a little bit, right here, you see that eventually it gets up to our final current. I was trying to change it from 0 amps to 3 amps, and eventually it's going to get up to that 3 amps. And when it gets up to 3 amps, what we see is that the inductor stops fighting. If I look at the current as a function of time, if it gets up to where it's 3 amps, 3 amps, 3 amps, 3 amps, when I look at this formula, the EMF, the magical battery, is minus the change in current divided by the change in time. Well, if I'm going from 3 amps to 3 amps to 3 amps to 3 amps, that's 0. Now, what that means is that right after I close the switch, the current through that inductor is 0. It acts like an open switch. If I wait a long time after I close the switch, it stops fighting, and the voltage across it is 0. And now it acts like a wire. Well, that sounds familiar. When we were dealing with capacitors, they acted like wires when I first closed the switch, and open switches a long time after. So an inductor acts just the opposite of a capacitor. If you understood how to put a capacitor into a circuit, an inductor is no different. Well, it is different. It's opposite. It's opposite. So now I showed you this video several times, and now finally we're able to understand what's going on. Okay. In a city, there are connected to the grid lots of transformers. And a transformer, you learned in your textbook, was just a pair of coils that were coupled to each other. And I could take a very high voltage and turn it into a low voltage. It turns out that when we take power across, say, a desert, we want to do that at a very high voltage so that we don't lose as much energy. And then when we get to your house, we don't want tens of thousands of volts where your children live. And so we convert that down to 110, 120 volts. And then we do that by having a transformer where we have a lot of turns in one side and fewer turns in the other side. And that steps down the voltage. Now, because there's so many coils in a city, there's a lot of inductance in the city. It doesn't want to change the current through that grid. And that's what they were trying to do here. They were trying to disconnect the power supply from the city grid. And all those transformers, all those coils said, oh, no, you don't. Just like your waffle iron, only in a bigger way. Okay, you know that had to be hundreds of millions of volts. And that came out of this equation here. See if your neighbor's on the bus. Just do a buddy check real quick. Can I get helpers? Gonna be my helper. Thank you. Helper over here. Anyone? Thank you for your service. Okay. What we have here is a sample exam, an old a sample exam question, I should say. This is from an old exam. And on the back, you'll find a similar problem that's straight out of one of your sample exams that I posted at Max. Okay? And we'll see how far we get through these questions. Yes, Miriam.
Does self-inductance means I'm making my own induced current?
Yes, you're fighting the change in current through yourself if you're the coil. Okay, so I'm a coil. Someone tries to change the current from 0 to 3, and I say, no, you got to do that gradually. I'm going to make you wait. Okay. Now, thank you so much. Does everyone have one of these pages? This row didn't get any. Oh, it's you. No. Okay. Now, again, I'll make you a promise. There will be a problem on the exam like this that has an inductor in it. There will also be on the exam a problem like this that has an inductor and a capacitor in it. And so you should be able to know, you should know how to handle either of those problems. So let's look at this one that just has an inductor in it. Again, just like with capacitor problems, there's 3 times that we can talk about. We've got an A and a B and a C. Okay. Zoom out, zoom out. Okay. Oliver. Okay. So we've got an A, a B, and a C. And part A tells us that immediately after I close the physical switch. Okay. Now, if this were a capacitor in there, I would say it acts like a wire, but it's not a capacitor, it's an inductor. And so an inductor, when I first close the switch, it acts like an open switch, forcing the current through it to stay 0 for just a little bit, And so if I replace that with an open switch, I know that all of the current through the battery has to go through the other path. Okay. And so if I'm asked, what's the conventional current going through that battery? Well, I just use V equals IR. Let's do that. Okay. I say V equals IR. And when I say V, I mean the change in V across the battery. And that's going to be the current through the battery. And that's going to be, the resistance will be the equivalent resistance of the circuit. Well, I've got a 200 volt battery. And I've got a total resistance along this path of 50 ohms. And that's going to give me a current of 4 amps. And of course, that 4 amps would be up. Because it's conventional current that we're always talking about. What's the voltage difference? You can see that this is an old question from years ago. What is the voltage difference across the inductor? Well, we said that the inductor is acting like an open switch or an empty light socket, where I take out the bulb and leave the gaping hole behind. How do we find the voltage across an open switch or an empty socket? Look away from what? Look away from the sun. Look away from the sun. Okay, so I want to find what the voltage difference is from here to here. From point A to point B. Now, I know that I've got 4 amps coming down here. And so 4 times 45, let me do V equals IR locally from A to B. And so that's going to be 4 amps times 45 ohms. That's going to be 180 volts. Well, let's check that that's right. If I've got 180 volts here, I better have 20 volts here, because 180 plus 20 is 200. Well, again, I've got 4 amps going here. 4 times 5 is 20. It works. Now, anything that's parallel has to have the same volts across it. And so that means the voltage difference across the capacitor will also equal 180 volts. And it's going to be oriented like that, such that it's pushing back against the real battery. Okay, fighting any current coming down that path. Yes.
Is that an open switch or does it become a battery?
It's an open switch, but we found that open switches have voltage across them like a battery. They just don't have chemistry to keep the voltage. Okay. So I can ask, what is the polarity of that switch? Which side of the switch is the positive side and which is the negative side? Okay, that sets up that pressure difference. Okay, now we wait a long time after the switch is closed. Well, if this were a capacitor, it would act like an open switch now, but it's not. It's an inductor. It acts the opposite. When I wait a long time, my current has leveled out. It's not changing anymore. There's no change to fight. And so it stops fighting. And so the voltage across that inductor becomes 0 and it acts like a wire. Well, now I know what happens if I put a wire across R1. I'm shorting out R1 and all of the current's going to go through the wire, the inductor, and none of it's going to go through R1. Well, now what's the current through the battery? Well, if I use V equals IR, again, doing it for the battery, I've got 200 volts, and now the whole resistance is in R2, which is 5 ohms, and so that's going to give me a current through the battery of 40 amps up. And the voltage difference across the inductor is 0. How do I justify that? Well, the EMF across the inductor, that's just the voltage difference across the inductor. That's gonna be equal to minus L times the change in current time divided by the change in time. And if I wait long enough, there's no change in current through that inductor. And so I get 0. Now, you'll notice that I gave you the inductance of that inductor in henries. And henries, if you think about it, is just, if you think about the units, is just Webers per second, Webers per amp, I'm sorry. And we're never gonna need that. We're never gonna need that. The only time we use this equation is when we're arguing that the voltage must be 0, because current's not changing. But I'm never going to have a situation where I'm going to plug in the value of L, okay, in one of my problems. What is the magnitude and direction of the conventional current through resistor R1? 0, it's shorted out. How we doing? Check on your neighbor. Okay. You remember that when we were talking about capacitor, I mentioned that they could be very dangerous because you could charge up a capacitor bank and then take it back to the storeroom, set it on a shelf, and it could just sit there for weeks. And then some poor grad student would be going to grab that off the shelf and pow, it would get them. It stores that energy while it's sitting on the shelf. Turns out that inductors are also dangerous, and we're going to find out right now. If we leave that switch closed for a long time, so that I've got 40 amps running through that inductor, and then I throw open the physical switch. Well, suddenly, R2 is no longer part of the circuit. Okay, there's not a complete path through R2. And the battery is not part of the circuit. The switch is not part of the circuit. This is just going to be the circuit right here. And so now, what's going to happen is that inductor, it says, look, you can't change the current through me instantly. A moment ago, I had 40 amps running through me going down. I still got to have 40 amps going through me when you throw that switch open. Well, how's it going to happen? It's going to happen because the inductor is going to generate an inductance that's going to push 40 amps around that loop right there. Now, I could figure out how big of a battery it turns into with this equation if I knew how the current was changing with time, but I don't. All I know is that that battery that suddenly develops through Faraday's law has to drive 40 amps around that loop. So if I use V equals IR, so I've got to have 40 amps going up through R1, and the voltage across the inductor has to be enough to drive that 40 amps through 45 ohms. So 40 amps times 45 ohms is 1800 volts. Yeah, that's the right response, 1800 volts, because it's got to do whatever it can to keep that current what it was right before I opened the switch.
The slide has the positive end of the inductor on the bottom, but then we drew it on the top.
Yes, because I drew it during part B. During part B, it was fighting any current coming, no, part A, it was fighting any current coming down this way, right? But now in part C, it's driving the current around clockwise. And so the polarity of that thing has to reverse, and it has to change from a 180 volt battery to an 1800 volt battery to keep 40 amps there. Now you can see that if I just change R2, if I suddenly change that to 1 ohm instead of 5 ohms, I've increased the current that has to go through that inductor, and now it becomes an even stronger battery. And so I can get huge voltages from these things.
Where did you get the 40 amps from?
The 40 amps. If I wait with the switch closed a long time, the inductor becomes a wire. And so all of the current through the battery goes through that wire and through R2. So the only resistance is 5 ohms, and that gave me the 40 amps. And that's what can't change instantly through the inductor. And that's why the inductor has to push so hard to keep it going. And it gets that huge voltage there. Okay, I think our brains are full. I think this is a good place to stop. Practice, practice, practice.
Excellent, good on, excellent today. Oh,
I think it's on the bus.